Quick intro. The purpose of testing is to find and address bugs before those bugs are found and addressed by users. Let's elaborate on the terms find and address. Testers find bugs by using testing techniques. Testers address bugs by bug reporting, and after the concrete bug is fixed, verifying that the bug was really fixed, and checking to see if new bugs have been introduced as a result of the bug fix. Users find bugs by using our website. Users address bugs by being pissed off and/or calling customer support and going to our competitors and/or filing lawsuits against us. Every time a user finds a bug, it negatively affects his happiness in being our customer. We, as testers, care about the happiness of our users, and we show our care by effective testing. Please note that if a tester finds a bug but doesn't address it, his testing makes no sense because an unreported bug will not be fixed. It's like having a winning lottery ticket and not taking it to the lottery organizers. The ideal situation is when the testing process discovers and addresses all bugs, but the truth is that ideal situations are often far from reality when we are dealing with software. Why? We cannot test 100% of software. There is a view on the purpose of testing which is widespread and harmful. It states testers must make sure that 100% of the software works fine. Let's discuss that. Here is spec number 1522. Program froggy.py accepts user input. Text of prompt for input: what animal do you like more, frog or cat? If input is either frog or cat, the program must print on screen, user input is a great animal. If user enters nothing and just presses enter, the program should print message, you didn't type anything. In all other cases, the message should be, you didn't enter the expected word. Here is a code of froggy.py written in Python. The text after the pound sign is a comment for the current line of code. Please pause the video and open up an attachment, froggy.py, to see the code. Now let's list the 4 possible inputs. Frog, cat, null input, any input different from input 1 to 3 inclusively. Brain positioning. Input can mean different things depending on the context. We'll use an incremental approach for a smooth introduction to this and many other concepts. For now, input is data passed to a system. From a user's perspective, the typical inputs are text, for example, username entered during login; file, for example, image file uploaded to a photo sharing website. Brain positioning. There are 2 kinds of input: valid input, invalid input. We need to know the validity of the input because software must process valid and invalid inputs differently. In the above example, valid input can be determined by looking at the user prompt. What animal do you like more, frog or cat? The valid inputs are frog and cat. All other inputs are invalid. In order to verify that 100% of the software works, we have to create 4 inputs and verify 4 actual results against 4 expected results. Test case number 1. Input frog. Expected result: frog is a great animal. Test case 2. Input cat. Expected result: cat is a great animal. Test case 3. Input nothing. Expected result: you didn't type anything. Test case 4. Dragon. You didn't enter the expected word. Wait a minute, why are we so sure that dragon covers all variety of possibilities called any input different from input 1 to 3 inclusively? Our confidence comes from the fact that looking at the code of the extremely simple program, froggy.py, we saw that all inputs except frog, cat, or null will be redirected by else to the output, you didn't enter expected word. But as a rule, testers don't look into the software code at all. Why? Because, on the one hand, the programmer and tester usually receive the spec at the same time, so when the tester starts writing test cases, there is no code to look into. On the other hand, software usually has thousands of lines of code, and even programmers cannot be sure how it will actually handle each possible input. So let's assume that we don't look into the code. How can we verify that 100% of the program, froggy.py, works fine? We have to test all possible inputs in addition to inputs from test cases 1 through 3 inclusively. By the way, if the language of our input is English, we can type 94 printable characters. Letters A through Z lowercase and A through Z uppercase, numbers 0 through 9, and special characters, punctuation, and symbols, for example, comma and $sign. Space, produced by the spacebar on a keyboard. If we test the condition, any input different from input 1 to 3 inclusively with one character, we have 95 possible inputs. But what if a user enters 2 characters? In that case, we have 9,025 possible inputs, 95 times 95. What about 3 characters? We have 857,375 possible inputs. That's 857,375 test cases. How about 10 characters? That would be an enormous possible number of inputs. So even in the case of a trivial task to test user input that's different from frog or cat or nothing, there is an unthinkable number of possible inputs. But the real pain only starts here. The basic concept of the computer program is input, processing, output. We can look at this analogy. When somebody calls your cell phone, it's an input. When you look at the caller ID and decide to take the call or not, this is processing. And when, depending on your decision, you either pick up or don't, it's an output. In order to test processing, certain input must be fed into the program so we can verify the output. To produce output, processing takes certain logical routes or paths. For example, if this is my boss, I'll pick up, otherwise I won't. In our simple case, there are 3 pathways. Path 1. If the input is frog or cat, processing produces the output. Animal is a great animal. If the input is nothing, processing produces the output. You didn't type anything. Path 3. If the input is not frog, cat, or nothing, processing produces the output. You didn't enter the expected word. In case of the worthless program, froggy.py, each path is short, simple, and straightforward. In the case of real software, for example, software known as the Google search engine, processing is much more complex. Example, imagine that you are hiking in the park. You're walking along the trail and you see a fork with 2 trails, Montebello on the left side and Skyline on the right. You take the trail called Skyline and keep hiking. Half a mile later, you see another fork and make another choice of where to go, and so on. Now, if you took the trail called Montebello, it would have been a different route for you. To explore the whole park, you'd have to hike all the trails. Example, now imagine the same concept but on a larger scale. Imagine that you have to drive from San Francisco to New York City. I'm not talking about the shortest route, I'm talking about all possible routes. The combination of roads is probably not calculable. For example, you can drive to Florida, then go back to California, drive to Michigan, drive to Minnesota, drive back to California again, and only after that, drive to New York City. The programmer who gave me that example said, "You know it took 200 years to build all those roads, but I can spend 20 seconds programming and get the same insane number of paths inside my program." So, in the case of real software, processing can contain tens, hundreds, and thousands, or even millions of unique logical pathways that must be tested if you want to test 100% of the software. What's important here is, in the case of inputs, you usually can determine a piece of data that represents some class of values. For example, Dragon represents the class any input different from input 1 to 3 inclusively. So if the processing of the input Dragon produces the expected result, you can assume, without being 100% sure, that the input XYZ minus 4% T would produce the same result. In the case of logical paths, you usually cannot say that path 1 works if path 2 works. In order to say that path 1 works, you have to actually test that path. Therefore, on top of an enormous number of possible inputs, we have an enormous number of possible logical paths. Let's pour some more salt on the wound. In addition to inputs and logical paths, we have conditions. Conditions are presets and/or environments under which the software is in use. For example, the same test can produce different results if you execute it using different web browsers. For example, Google Chrome version 59.0 and Firefox version 54.0. First condition is test case is executed using Google Chrome version 59.0. Second condition is test case is executed using Firefox version 54.0. So, in order to test 100% of software, not only do we have to test all inputs and all logical paths, but we also must execute them in each version of each web browser known to humans. Brain positioning. Looking at the enormous mountain of possibilities produced by a combination of inputs, logical paths, and conditions, we can clearly see that it's usually impossible to test 100% of the software. In other words, testing usually cannot cover 100% of the possibilities of how software can operate. Therefore, we can either set up a 200-year plan to test software that probably no one will need in 10 years, or we can be smart testers. Brain positioning. Whether we like it or not, there is always a probability that bugs will be missed by testers. But we, software testers, can substantially reduce that probability by working hard and, most importantly, smart to find and address bugs. Testing and quality assurance. Brain positioning. The purpose of quality assurance is to prevent bugs. The purpose of testing is to find and address bugs that have not been prevented. Quality assurance and testing are similar because their common mission is to improve software. Quality assurance and testing are different because quality assurance improves software through process improvement. Testing improves software through bug reduction. Although our course is focused on testing, we also look at many issues from the quality assurance angle. Why is process improvement so important? Because software development is a process, more precisely a set of processes, and thus software quality has its roots in two things. One, how quality-oriented our software development process is, and two, the mentality and actions of each participant in the software development process. This brings us to the important idea that testers and quality assurance engineers alone cannot be responsible for software quality. You can be held responsible only for things that you fully control. For example, if a spec has a bug, that bug can be incorporated into the test cases and the software code as a legitimate thing. But what is so special about testers and quality assurance engineers then? Our mission is to be passionate advocates of constant quality improvement in any shape and form. While we cannot be in full control of software quality, it's in our hands to go above and beyond promoting quality as a vital philosophy within a software company. Lesson recap. The purpose of testing is to find and address bugs before those bugs are found and addressed by users. Testers find bugs by using testing techniques. Testers address bugs by bug reporting and, after the concrete bug is fixed, verifying that the bug was really fixed, and checking to see if new bugs have been introduced as a result of the bug fix. Testing usually cannot cover 100% of the possibilities of how software can operate. Quality assurance is targeted towards prevention. Quality is a group effort. Each person involved in software development is responsible for quality. Quality is directly affected by the effectiveness of the software development process.